So our next talk will be EasyUC, using EasyCrypt to mechanize proofs of universally composable security by Ali Stoughton.
Stoughton, right. So this is joint work with my BU colleagues Ron Kennedy and Mayank Varia. And background, securing systems is of course hard, especially those built using cryptographic schemes and protocols. And doing this all in a single go is unrealistic. So instead we need a modular approach. And even with a modular approach, pencil and paper mathematics is imperfectly able to cope with the complexity of the proofs, and so we want some kind of proof mechanization. And we're going to be working within the universally composable UC security framework of Kennedy and others, which is a refinement of the real ideal paradigm that supports modular proof development. In UC, a protocol interacts with two entities, an environment which supplies protocol inputs and consumes their outputs, and an adversary that's given certain powers to observe or corrupt the protocol, and the environment and adversary can work together. UC uses what I would call, as a PL person, a coroutine style of message passing, in which control is transferred along with the data, and the environment drives the show in UC. A protocol consists of one machine for each protocol party, and an ideal functionality consists of a machine together with some dummy parties that communicate pass inputs and outputs to and from that machine. And somewhat non-standard terminology, we're using the term functionality for both protocols, so-called real functionalities and ideal functionalities. You've probably seen this, but a real functionality UC realizes an ideal one if and only if for all adversaries there's a simulator such that for all environments, the environment can't tell if it's interacting with the real game, which is the real functionality and the adversary, or the ideal game, which is the ideal functionality and the simulator wrapped around the adversary. More precisely, the environment is yielding a Boolean judgment, and we want that the absolute value, the difference between the probabilities of it returning true in the real and ideal games be negligible. And this definition generalizes to the case where the second functionality is arbitrary, might be a protocol. And UC emulation is trivially transitive. That's one of the cool things about it, because the simulators just compose. So then if Q is a functionality making use of a functionality R, and S is compatible with R, then Q with R changed to S, that's the UC composition operator, is the functionality in which calls to R are replaced by ones to S, and then we get the UC composition theorem, which is what supports modular proof, which says that if S UC emulates R and Q uses R, well, if we change Q to use S instead, that will UC emulate Q. So that's a quick background on UC. So compatible here means that they've got the same kind of interface in terms of the dummy parties or the real parties. So, and we're going to be working in the sequence of games approach, and so the game hopping approach. And so, of course, in this style, each step in the trek from the real to the ideal game has a cost to it, and you sum all those costs to get the overall upper bound, the overall strength of security. So what about proof mechanization? I'm going to be really brief here. There are several very good frameworks, I think, for doing computational model proofs of complicated protocols. The one that we're going to be using is EasyCrypt, which is a standalone proof assistant with a fairly small and well-studied PCB. Manuel mentioned it. We're using EasyCrypt largely for reasons of familiarity and affiliation. I'm not going to make any strong claims that the others wouldn't be good vehicles as well. And in EasyCrypt, cryptographic games are modeled as modules, which consist of global variables and procedures. They can be parameterized, like by adversaries. Now, procedures are written in a simple imperative language with while loops and random assignments. There are four logics in EasyCrypt. And let me say here that one can prove a probabilistic relational horologic lemma about a pair of Boolean returning procedures and then use the ambient logic to move that relational proof into one relating the probabilities that the procedures return true, a typical kind of move that one does. And then finally, proofs in EasyCrypt are structured as sequences of lemmas. You prove individual lemmas using tactics, as in Coq. You can group definitions, modules, lemmas together in what are called theories and then specialize them by a process that's called cloning. So what are we doing? Well, we're in the early stages of researching how UC security can be mechanized in EasyCrypt. And a major and initial challenge is how to deal with UC's coroutine style of communication in what is a procedural programming language. So our approach is to give functionalities addresses, just lists of integers like mailing addresses, and to build abstractions that route messages to their destinations. Messages can be direct, providing inputs to functionalities or reporting their outputs, or adversarial for communication between the environment and the adversary, but also the functionality and the adversary communicating. Now, EasyCrypt has modules, as I mentioned before, and so it's natural, I believe, to realize functionalities as modules, real or ideal, real protocols or ideal functionalities as modules. And so in this way of thinking, the parties of a real functionality all live under the same roof, all within the same module. And this makes it natural for functionalities to have sub-functionalities with sub-addresses, and a parent functionality can guard those sub-functionalities, deciding what to forward on from the environment to their children, protecting them. Modules in EasyCrypt may be parameterized, and that means that UC composition can very simply be realized just as module application, which is really nice. And when we need multiple instances of functionalities, we replicate them using this cloning process. So we can just fire up statically as many of these things as we need. How do we connect a functionality and adversary to an environment? Well, via what we call an interface, which is a router, and it's also functioning as a firewall. The sources and destinations of messages are actually ports. So they're pairs of addresses, lists of integers, and then integers, which we call the integers I port indices. They're kind of entry points into a functionality, you can think of it. Here in this picture, this is saying that the functionality knows it's at address alpha and that the adversary can be addressed at beta. That's what that means. The adversary knows it's at beta, and this is the root address of the environment sitting up here. And indeed, the most common channel of communication between the environment and the adversary is between this port and that port index of beta. So messages can flow back and forth like that. There's this thing called an input guard in the interface, and I'll explain that in a second. So there are kind of three message flows that can happen. The environment can send direct messages down this branch and adversarial messages down this branch, but not the other way around. And the function of the input guard is to control what ports of the adversary are accessible to the environment. 0 is always accessible. That's that standard communication path. But here 1 is being exposed as well. And the reason we might do that is to support composition, as we'll see. Because, well, so it would be 1 comma beta, I guess, and but the adversary just has a single address here, and this is meaning port index 1 within the adversary, within beta.
And how does the environment
Inputs to alpha will go down like this. There'll be direct messages. Adversarial messages are flowing like that.
That's when the part
because I don't need to control what can flow this way, but I need to control what can flow that way. So bear with me for a second. The functionality can send direct messages up like this, and adversarial messages like that, but not the other way, and it can't talk to the special port index because that's reserved for the environment. Finally, the adversary can send adversarial messages like this and adversarial messages like that. The way that we nest adversaries inside simulators is illustrated here. We have the ideal functionality over here. We have the environment up here. And the ideal functionality, when it talks to the simulator, like in this picture here, this was the ideal functionality, it's talking to this port index. That's where the simulator is going to be entered. But the environment, when it sends to 1 and 0, they just flow through the simulator. So the simulator is written to just forward these messages on. So there's a clear channel like this, but messages from the ideal functionality are caught by the simulator. The simulator can then do real functionality spoofing, trying to pretend that it's really the real functionality. So that's how these port indices come together to do simulators. So how does this stuff get realized in EasyCrypt? I'm not going to show you a lot of EasyCrypt code, but there are these module types here, types of modules. So a functionality implements this type that's here, meaning that it has two procedures, init and invoke. Init is given the address of the functionality itself, as well as the address of the adversary, and it should initialize any state that the functionality has. And then at runtime, invoke is called with a message destined for that functionality, and eventually what does it return? Well, either an error or an outgoing message, one that's going to be routed by whatever outside the functionality to its destination. And adversaries, perhaps confusingly, have the same interface. And so they're also implementing this, but we're not going to call them functionalities. But they in the system, they act in the same way. And simulators transform adversaries into adversaries, as we saw before. What about interfaces? Well, they implement this module type. So they also have an init procedure, which takes the address of the functionality, the address of the adversary, and whatever the input guard is supposed to be. And that's when it's called, it will initialize the adversary, the functionality in the adversary, as well as initializing its state. And then at runtime, invoke works as you'd expect. The environment can call it, and eventually either an error or an outgoing message comes back to the environment. The environment is implementing this interface, parameterized by an interface. It's got a main procedure that takes the usual data, just like the interface. In the end, it issues a Boolean judgment. And how can it interact with the interface? Well, only via the invoke procedure. So this is EasyCrypt syntax to say the environment may not reinitialize the interface. So how do we make an interface? Well, we have a router that I'm not going to show you that takes a functionality and an adversary and puts them together into an interface. And then an overall experiment, which is parameterized by an interface and an environment, works like this. Its main function takes the usual arguments, it initializes the interface, and then invokes the main function of the environment, letting it experiment with the interface as many times as it likes. Eventually, it returns a Boolean judgment, which is returned as the result of the experiment. So a kind of typical setup in EasyCrypt, apart from the fact that the environment is really driving the entire computation here. So how are we testing what we're doing? Well, I just finished a first proof, first case study proving security of secure message communication in a UC style via one-time pad encryption, where the one-time pad is agreed by the parties using Diffie-Hellman key exchange. And so we've got a group of Diffie-Hellman keys with a generator in particular here. We've got a commutative semigroup of Diffie-Hellman exponents. We've got a way of raising a key to an exponent, getting a key. And every key is uniquely determined from the generator by exponentiation. And we've got this usual axiom here. But in addition, they have a type of plain text, an injection into this group of keys, and a partial projection back the other way. So sometimes some keys they project to an error, but we don't care about that as long as the things we inject behave well, then we're fine. And so I'm sure you can see where this will go, but secure message communication here works like this. The parties use Diffie-Hellman key exchange to agree on a key, K, and then party one takes its plain text, injects it into the group, and uses the group operation with the key K to get the encrypted message, sends it over the wire, and we have a model where the adversary can see the transmission, but it can't corrupt it, so it's not allowed to make changes to the message. To decrypt, we just use the inverse of the key and the group operation, and then project back to the plain text. And of course, Diffie-Hellman key exchange, both of the parties have their own private exponents. Party one sends this to party two, party two sends this to party one, and then they use their private exponents to resolve, to reach the same point of the shared key. So how does this work in our setting? Let's start with the ideal functionality for this one-time communication. So SMC ideal, and so this is meaning that it's at address alpha. It thinks the adversary is at beta. It's willing to accept direct messages on this port index 1 and adversarial messages on 3 and nothing else. That's its kind of guard. A message comes from the outside world, from some port ID 1, into here, saying what the plain text is and where it should go, ID 2, and the ideal functionality says, okay, well, I'm going to send a message, an adversarial message off to the simulator, which by convention, it's not hardwired in the code, but let's say it's at port index 3 of beta, and so the simulator gets the identity of the two ports, ID 1 and ID 2, the source and target ports, but of course not the plain text. It has to do its work without knowing the plain text. Eventually, control comes back to the ideal functionality, and then it simply sends the original plain text that it had saved by a direct message back to the recipient, ID 2, saying it came from ID 1. So that's how the control flow works in the system. To tell you about the real functionalities, I need to start from the bottom up. So first, a forwarding functionality, an ideal forwarding functionality, foff, or a version of foff for people who know this in the literature. So here, a direct message can come in from the outside with a value to be forwarded and where it should go to ID2. And the forwarder says, okay, I'm going to tell the adversary at port index 1 for forwarding control, this is what's being proposed, that ID 1 would like to send V to ID 2. What about it? The adversary eventually, hopefully, will return an OK message by an adversarial message to us, at which point we'll say, OK, great, we're allowed to do the forwarding, and we'll send that value on to ID 2 saying where it came from. So that's this building block that we use to do forwarding between protocol parties. And then we can use that, we'll use that in a minute in the real functionalities. The ideal functionality for key exchange is kind of like the ideal functionality for SMC, except there are two phases to it. That ID1 can initiate a key exchange and come in to here. We'll go off to the simulator at port index 2, bounce back, but then this shared key will get sent from here to ID2. ID2 is then responsible for reciprocating and bouncing back into here. We'll go back to the simulator, back to here, switch to here, and then the key will finally end up back at ID1. So this programming in UC is a little bit different, that control flows with messages, and so these two phases have to work like that. The real functionality for key exchange is the same kind of interface as the ideal one, except inside it, it's got two protocol parties and two sub-functionalities for forwarding. So here, party 1 is managing the external port 1, party 2, the external port 2, just like we had 1 and 2 on the previous slide here for the ideal functionality, but party 1 also has an internal port, 3, and party 2 has an internal port, which is 4. And these forwarding functionalities are used to forward messages between 3 and 4 and then back the other way when it sends G to the U1 from 3 to 4 or G to the U2 from 4 to 3. These things are mediated by a forwarder. The parties are not allowed to talk directly. They have to talk via the forwarder so the adversary can actually observe what's going on. Otherwise, we wouldn't be playing fair as a real functionality. And then what about SMC real, the real functionality for secure message communication? This is parameterized by some arbitrary key exchange functionality. Yes. Yeah, that it's authenticated channels, and this is how we let the adversary see what would be going over the wire, over the network. So in SMC real, so we had 2 forwarders here, but now we've got a forwarder for forwarding the one-time pad encryption, and between these internal ports 3 and 4 of party 1 and party 2, but then we also need some way of doing key exchange. And the beauty of this is that KE is a parameter to this, that it could be real or it could be ideal. And the functionality is written in a way that's completely agnostic to what it is. Between 3 and 4 can use KE in these 2 phases to agree upon a key, and then that key can be used by party 1 to send the one-time encryption from 3 to 4, and then party 2 can finish up by decrypting with the key that it now knows. So that's the picture. But again, let me just emphasize that SMC real has this argument that's KE. It could be some other functionality that doesn't even do anything sensible. The routing code that's inside this doesn't care, but of course you'd want it to do something sensible, or it wouldn't do anything very interesting. And in the case where this is the ideal functionality, then messages are of course going to the port for key exchange, the key exchange simulator, as well as the forwarder is communicating to port 1 of the adversary. So tour through the proof. So when we prove key exchange security, then we're relating these 2 experiments here, KE real and the adversary and the environment, to KE ideal and a simulator wrapped around the adversary and the environment. And the simulator is diagrammed here. The adversary is responding to these messages to these 2 port indices, 1 and 0, which are just passed through by the simulator. But the ideal functionality communicates to the simulator on this port index 2. It also pretends to be the real functionality's forwarders. So we had these 2 forwarders within the real functionality for key exchange, and there's this dance where the simulator is pretending to be these forwarders and interacting with the adversary. That's how it tries to convince the adversary and the environment that it's really not the real, that it's the real functionality. What's important to make this proof work is that 2, which is this way of the ideal functionality communicating with the simulator, must not be in the input guard. So that's what the firewalling is doing. It's protecting us from the environment seeing into the workings of the simulator, which would obviously let it tell the real and ideal games apart. In the proof, it's a sequence of games where we start at the real side, we want to end up at the ideal side, and we get to a point in sort of the middle of the sequence of games where we've got commonality, except on the left side of the gap, we're using G to the U, G to the V, and G to the U times V. On the right side of the gap, we're using G to the U, G to the V, G to the W, where U, V, and W are randomly chosen and only used once in these circumstances, only used in exactly the circumstances. And this lets us reduce this game transition to the decisional Diffie-Hellman assumption. And our upper bound that we get is the reduction. It's a constructed adversary built out of the environment and the adversary. So the DDH adversary we build mechanically, textually, out of the commonality at the point of this gap, plus which involves using the environment and the adversary because they're part of this commonality. So that is the reduction. Crypto people sometimes find this a little bit confusing, that the reduction is this concrete adversary for DDH that we've built. And the other game transitions all have upper bounds of 0. In fact, this is the only computational part in the whole proof. Then we have to lift that security theorem to the context of SMC real. So we've got KE real and KE ideal. We've got this bit in blue that we've done a proof about, but we want to use it in a context. This is an instance of the UC security theorem. And how do we do that in EasyCrypt? Well, we apply key exchange security to a composed environment that's built out of this experiment that's here. So it's got SMC real within it. And then these mysterious stubs for key exchange in the adversary, which I'll show you in a minute. So basically, the core of making this work is a bridging lemma that involves showing the equivalence of this diagram with one I'll show you on the next slide. And so here we've got SMC real, and we've got some kind of key exchange functionality. It doesn't matter which one. Here we've got an adversary. This could be KE ideal, and this could be the simulator wrapped around the adversary. This could be KE real and the real adversary. This proof is going to be parametric, though. It doesn't matter. It doesn't have anything to do with the simulator. We can do this abstractly. We've got an interface which at the top level has some interface. What's important at the top level is this not have to, which was the special way for the ideal functionality of the key exchange to talk to the key exchange simulator. We want to show an equivalence between that and this. And so what's happened? Key exchange and ADV have been moved down to this interface that's here. And they're talking to a composed environment that has the real environment inside it. Here we've got SMC real of this KE stub and the forwarder, and we've got the adversarial stub sitting over there. And we have the interface here, the guard is X, just like it was outside. But down here, we've got a Y, which can be a superset of that. And so what do the stubs do? When a message comes into them, they just forward it down to the interface. So something that should go to the adversary flows like this. Something that comes into here can flow like that. They're just forwarding down to the lower part of this diagram. But there are a couple subtleties. One is the forwarder needs to be able to talk to the adversary when doing forwarding. Here, that path will go like this. But to get through this interface, it has to be that Y has the forwarding port in its guard. And so we need to be able to add one into Y here, but we don't want one to be in X. We don't want that to be in the statement of our theorem at the top level. But this is general, that as long as all the extra things that need to talk to the adversary are in this guard Y, then we're golden. Everything works. The other subtlety is sort of amazing sleight of hand. That suppose a message comes down this path to here, and this communicates to key exchange, and key exchange says, I want to return a direct message as if it came from there into SMC real. How does that happen? Well, we've come like this, and so we would have to return up to here. And that's of course not where we wanted to return. We're following the procedure call stack. So what happens? Well, this stub says, oh, I just had a direct message returned to me. That's not what I normally get. I'm going to save that in my shared state with the other stub, my partner in crime. I'm going to send an adversarial message across to here and wake up the stub, which says, oh, I've been left a message. I should just return it as if it came from me in the first place. And a similar thing happens the other way around. So even though EasyCrypt has this procedural semantics, a little sleight of hand here in this bridging lemma, it's not something that we have to actually run, it's just part of the proof, manages to finesse this detail. So we put that together with doing key exchange security, just applying it to this composed environment. So this is the right situation for key exchange security. That gives us the first step of our top-level proof. The second step is the one-time pad argument. We're going from SMC real of KE ideal and some adversary ADV prime to SMC ideal. So going like this, that's the one-time pad argument, totally bread and butter for EasyCrypt, the random tactic in EasyCrypt. We have to construct a new simulator, but that's a similar kind of effort to constructing the one for key exchange. Here, it needs to be the case that the guard doesn't have the special port of the SMC simulator in it, which let's say is 3. So 2 is key exchange, 3 is SMC. And then, what do we do with this? Well, we say, we've proved this for an arbitrary ADV prime. Let's plug in for ADV prime KE sim of AV. And so simply taking this picture here and plugging in that substitution gives us this. And we already have the instance of the composition theorem. This is saying we could start out here, go to there, which is equal to that. These are the same. And then go to our final resting point. So we compose these two, gives us our top-level theorem, which is there. So we've stacked up the simulators. It's the beauty of this method, that the simulators just keep stacking one on top of the other. Messages flow through the simulators to the appropriate place from the ideal functionality. And then the back way from the adversary, they get caught at the most local point that knows how to respond to them. It's quite beautiful. I think here the overall bound is the DDH one, but for this composed environment, since we applied key exchange security to compend, well, that's the one that's part of the bound. And the overall restriction on the guard is exactly what we'd hope. It just says that the environment can't mess with these simulators, which if it did, it would be trivially able to break security. Right. So as Manuel said, there's nothing in EasyCrypt that does this automatically. What we need to do, among other things, is look at the simulator code and look at the constructed adversary and check that they run in time that we think is acceptable and don't do like discrete log. So let me just finish. I'm sorry, I'm almost out of time. The case study is complete. It validates our architecture and approach, but we need some changes to make it scale up. One is we need a way of doing guided symbolic evaluation to let the real and ideal games co-evolve. And I think I'm not going to be able to talk about that much, but at the moment we basically have to run things inside the tool, run programs using EasyCrypt's proof tactics, and we need a way to automate that. We need a way of automating the bridging lemmas, but otherwise the methodology for composition is completely general, and either we can do a proof at the level of the meta theory and then add it to the TCB, or we can maybe automatically generate the proofs so we don't have to change the TCB. And then finally, we'd like to have a domain-specific language for expressing functionalities, meaning that crypto theorists won't have to look at a bunch of ugly EasyCrypt code. Type checking will catch a lot of errors. It can be the bridge to the cock verification of the code for protocol parties. In the short term, we're going to translate into EasyCrypt. In the long term, we'd like to integrate it into EasyCrypt. And I'm done. So there's the GitHub repo if you want to look at it. And did we run out of time? So no time for questions? Or Elaine? So
can you explain more how you are going to deal with this polynomial runtime issue?
Yeah, so if we look, for instance, at the simulators, then we actually have to inspect them manually and convince ourselves that they run in whatever time we want them to run in, and that they don't do things that are inappropriate in terms of, so there is no cost model in EasyCrypt. For the constructed adversaries of the reduction, we need to make some assumptions about the power of end and av, and then look at the code again and convince us that they behave in a way that we like. EasyCrypt doesn't help us with that. There's no cost model.
Fair, but I just want to add to that, what is, from the crypto side, from what I understand, EasyCrypt gives you is an explicit reduction from, in this case, between a distinguishing environment and an adversary that breaks DDH. And then it's up to us to inspect the reduction and see that it's one time or to our liking. But it gives the reduction. Yeah,
that's what I was trying to say, that the reduction is this DDH adversary, which is concrete code, a concrete module, and you can look at it. It's in terms of the environment and the adversary, and so you need to make some assumptions about them to be able to then reason about what the combined adversary for DDH can do.
Talk more offline. Like we have also been trying to do some of this, and I guess we have some. We encounter some things that we think is like difficult.
No other questions? Thanks.